Hello, good morning, good evening, good afternoon, everyone, depending on what time you'll be watching this. My name is Mgavi Samuel. I'm doing Masters of Science in Computer Science, and I'm going to be taking you through this paper, reviewing this paper, Enhanced Supervised Extreme Learning Machine-Based Method for Non-Linear Fault Detection. Contents of the presentation are those, and allow me dive straight right into the abstract or the introduction. Now, you realized unsupervised extreme learning methods have been used before, but all these methods experience these problems. They are only designed to preserve the local adjacency similarity of the input data set instead of mining the intra-class variations. Then also, the other problem faced is that determination of the optimal unsupervised extreme learning hidden nodes. We're going to be talking about hidden nodes later. Is a tough issue. And this paper is mainly showing how we shall enhance these unsupervised extreme learning machine methods so as to better approach these problems. This is the proposed unsupervised extreme learning approach we shall be taking, naturally incorporating the diversity analysis technique into the original unsupervised extreme learning objective. We're going to talk about that. The Kano trick is then employed on this in the enhanced unsupervised extreme learning approach. Then, based on the extracted diversity and local similarity, low dimensional feature information like the KNN is applied, and lastly, experiments of comparison between these different methods are given, and graphs and tables are shown in the paper that we are reviewing, showing how the comparison, how this method measures up with other approaches that were previously used. Let's first understand what extreme learning machine algorithm is. If you're interested in the math, that is the formula, but for me, I understood it mainly from this diagram. So you have these inputs. What we are seeing here is the input nodes. And on these inputs, we randomly assign weights and biases. Now, out of these weights and biases, we calculate what we call the hidden layer. This is the hidden layer we were talking about in the introduction. So we get the hidden layer out of the weights and biases from those variables. Now, out of that hidden layer, we have to come out with a weight matrix. And it is this weight matrix that we use to predict the output nodes on new data that will be given. That is the extreme learning machine mainly for you. So the unsupervised extreme learning machine, its main objective, it guarantees probabilities of adjacent inputs x1 and x2 to be similar, they should be similar in the output space, and it's enforced by following the optimization objective that is adopted. That is the math right there in the formula. Now, the enhanced unsupervised extreme learning model, it mainly optimizes the unsupervised, remember unsupervised extreme learning model, it optimizes that and works out outputs F1 and F2 so that the two neighboring input samples of X1 and X2 are also near neighbors. Mainly, it modifies the unsupervised extreme learning machine by integrating intra-class diversity information and also employs Kano tricks to the modified unsupervised extreme learning model. Let's look at the flowchart. Now, in the flowchart, this is how the methodology is applied. So you collect normal operating data and you normalize it. Then after that, construct matrices to build the unsupervised extreme learning model. Then establish the matrices using the training data set. After establishing the training matrices using the training data set, build an extreme unsupervised extreme learning, an enhanced unsupervised extreme learning method model by combining the diversity information kernel tricks. Then from there, calculate the projection, estimate the statistic, and finally this is what I would like to interest you mainly in. If the monitoring statistic, we have a monitoring statistic, if it exceeds the confidence limit, then a fault is detected by the model. These are the fault detection strategies that were supervised in, that were given in the paper. Statistic construction using the KNN principle and also the enhanced unsupervised model that we are discussing right now. A number of case studies were followed, one being the numerical nonlinear system, on a numerical nonlinear system, and the other on the Tennessee Eastman approach, which is very significant in this discussion. And in all these case studies, we had a process description, then the parameter setting, and after the parameter setting, we had the fault detection of the effects comparison. We shall look at that, the comparison of the two case studies. These graphs were drawn. There were very many graphs that were given in the paper, but these are what I really wanted to bring to your attention, that in the fault detection rate, sorry, the words might be a bit small. I know they can zoom that in. Unfortunately, it's not giving what I want. But in the fault, on these graphs, they show that after running the models, the graphs show that the fault detection rate was higher. We are mainly interested in this right bar, which is the enhanced unsupervised extreme learning machine. Its fault detection rate was higher than all the others, as you can see in the graph here. And it is also indicated here in this table. You can see that here, this is the unsupervised ELM, but then this is the enhanced unsupervised ELM. The detection rate is 99.98. Here it is 99.90. The enhanced unsupervised extreme learning machine being higher than all the rest. Then the fault detection time, it detects the fault earlier than the other models. That's why this red bar for the enhanced unsupervised extreme learning machine is shorter, because it detects the fault earlier and flags it than the others. So in conclusion, this paper brought 3 main contributions, and out of these contributions, and you have seen the comparisons between the different approaches, it all just shows the superiority of enhanced unsupervised extreme learning machine in fault detection, nonlinear fault detection, making it a better approach. Thank you for listening. Okay.